uh, so before starting this virtual session, I will review all the topics covered in face-to-face class through some questions. So let's begin with the first question. So if we have continuous and categorical attributes, how we can apply association analysis formulation to this data set? How we can resolve the problem of continuous attributes and categorical attributes? Transform to binary. No, not here we can transform to binary. So for continuous we can use intervals. Yes, that means we will make discretization. Not here mean a priori. So here for continuous attributes, we make discretization. That means we will use intervals. This is an example of continuous attributes. This is another example. And for categorical attributes, we can here modify the value by gender equal male. This example. So if we have many possible values in categorical attributes, we can merge the attributes or the values with a low support. The low support. Okay. So what are the types of categorization? What are the types of categorization? So, sorry, for discretization, what are the types for discretization? There is unsupervised with equal width, equal depth, clustering, or supervised. Okay? So for document term matrix, this is a document term matrix. We will apply mean a priori. But before applying mean a priori, we have to normalize this document term matrix. So the question is how we can normalize this matrix. For example, here the value 2 will be normalized to what? So 2, it will be normalized by 2 divided by the sum of the column. The sum of the column, or the sum. So 2 divided by 5, not 6 here. Okay? Here, for example, 1 will be 1 divided by 6. Yes. This, for example, this 1 will be 1 divided by 3. Okay. So, how we can calculate the support of a combination of word. We will use what here to calculate the support of, for example, we want to calculate the support of here W1, W3. Support of W1, W3. We have to use the minimum. Yes, the minimum. For each document, we will select the minimum, and after that we make the sum of these minimums. So here, for example, in our example W1, W3, we will focus our attention in W1 and W3. After that, for each document, we will select the minimum. So for example, here the minimum is 0 here, 0 here, 0 here, 0 here, and 0.20 here. So the support equals 0 plus 0 plus 0 plus 0 plus 0.2 equals 0.2. It is clear? Okay, after that we discuss the multi-level association rules and the sequence data. Here, because here we calculate the support between of W1 and W3. So for each document, yes, because here for each document we will make comparison of the support of W1, for example, for the document number 1. For document number 1 here, the support of W1 equals 0.4, the support of W3 equals 0. For this reason, we say that the first value is 0. After that, for document number 2, we have 0 and 0.33. For this reason, we have 0. For the last one, 0.2 here, 0.2 and 0.33. So the minimum is, Mr. Walid, the minimum is yes, all the row. Yes, the minimum is 0.2. For this reason, the support will be 0.2. It is clear? You're welcome. Okay, we discussed also sequence data. And here, what's the meaning of a subsequence? And we said that a sequence A1, A2, AN is contained in another sequence B1, B2, Bm, with M is more than N if there exist integers I1, I2, In such that I1 is a subset of Bi1, I2 is a subset of Bi2, 2 normally, etc. Let's move now to the sequential pattern mining definition. So we have subsequence data and we want to extract pattern from this sequence. So given a database of sequences, the user specified minimum support threshold. So minimum support threshold. Why the user has to specify this minimum? Why the user has to specify this minimum? So if we want to extract pattern from a data set, we specify a minimum. Why? Why we have to specify this minimum? Yes, we specify this minimum because our task is to find all subsequences with a support is more than this minimum. We want to select frequent subsequences like frequent item set. So given a sequence, we have A, B, C, D, E, F, G, H, I. So there are many examples of subsequences. This is, for example, is a subsequences. This is another subsequence. This is another subsequence. So how many K subsequences can be extracted from a given N sequence? For example, here, if we have N equal 9, and 9, that means this is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. And we have 4. 4 is the number of items. Here we have 4 items. 1, 2, 3, and 4. 4 items. So with 9 items and 4 events, we can find 126 possible subsequences. 126 possible subsequences. So here we have an example of sequential pattern mining, and we calculate the support of each subsequences, and after that we extract the frequent subsequences. So how we can calculate this support? So in our example, can you give me the object A, the sequence A? I repeat my question. This is my data. Can you give me the sequence A? 1, 2, 4? No, it is not 1, 2, 4. There are 3 A's here. 3A. Not 1, 2, 3, 5. So the sequence A is like this. A, and after that the first, A, This is the sequence. So the first one is, or the first event is 1, 2, 4. After that, the second, so this is the first one. Yes, very good. Yes, very good, Ammar. After that, 2, 3. This is 2, 3. And after that, 5. This is 5. It is clear? Okay. So we want to extract the support of this sequence. So can you give me B, for example, B here? The sequence B. B. One, two, 1, 2 together. After that, 2, 3, 4 together. Yes. Okay. So here there is an extraction of a frequent subsequences. So can you explain me why the support of 1, 2 is equal to 60%? So 1, 2 is the support is equal to 60%. Why? So here when we calculate the support of 1, 2, we will see how many. So why 2 divided by 3 is not 60%. We will count the number of objects here. We will count, very good, Rami. We will count the number of objects that contains 1, 2. So how many objects we have here? How many objects? We have A, B, C, D, and E. 1, 2, 3, 4, 5. So we will divide by 5. It is clear? So after that we will, yes, we will, yes. Here after that we will see what are the sequence that contains 1, 2. The A contains 1, 2, yes or no? Here, yes, A, 1, 2. The B, 1, 2, yes. The C, yes. The D, no. The E, no. So in this case, the support will be 3 divided by 5. Okay? It is clear? Okay. So let's count, for example, the support of another subsequence like this. 1, 2, 2, 3. So 1, 2, 2, 3 here, okay. 1, 2, 2, 3, okay, here. 1, 2, 2, 3, also okay. Here, no. And here, no. So 1, 2, 2, 3, the subpart equals 3 divided by 5. So how we can extract sequential patterns? Given n events, I1, I2, In, we will begin with candidate 1 subsequences like this. After that, candidate 2 subsequences. After that, candidate 3 subsequences, etc. So the step number 1, we will make the first pass over the sequence database D to yield all the 1 element frequent sequences. After that, we will repeat until no new frequent sequences are found. The first step is to generate candidate. Why we can generate this candidate? We will merge pairs of frequent subsequences found in the k-1th pass to generate candidate sequences that contain k items. After that, we make candidate pruning. So we will prune candidate k sequence that contain infrequent k-1 subsequences. It's like a priori algorithm, but here we will use subsequence, not item. After that subpart counting, we will make a new pass over the sequence database D to find the subpart of these candidate sequences. And the final step, we will eliminate candidate k sequences whose actual subpart is less than mine subpart. So this is the generalized sequential pattern algorithm. It is clear? Any questions?
Assalamu alaikum.
Yes.
Assalamu alaikum. Do you hear me, Doctor? Yes, regarding the this generalized sequential pattern.
Alaikum salam.
I think the approach is exactly like the one we use in a priori. We find K1,
yes,
K plus 1, and we convert, we scan for candidates.
Yes, yes.
And we convert to support until we find rules, yeah? But, yeah.
Yes. Yes, the same one. But here, there is a difference. When we merge, for example, in the previous chapter, when we have, for example, A and B, and we will merge A and this is one item set. A, B also is one item set. When we merge A and B, we will make like this, and we say that AB, and we don't create BA because here the order is not important. But for sequential pattern, when we merge pairs of frequent subsequences, we have also to illustrate all the possible orders between subsequences. For example, if I have a sequence I1 like this, and another one I2, so merging And let's suppose that sequences are frequent. When we merge these sequences, the merging two sequences will produce two candidates, I1, I2, and I2, I1. This is the difference between the previous or a priori algorithm to extract frequent item sets and generalized sequential pattern. Any other questions? Yes, we will see the graph now after the sequence. Now, so for the graph, there are other challenges because in the graph there are some other concepts like vertex, edge, there is a labeled graph, induced graph. So additional constraints are imposed by the structure of the graph. For example, frequent subgraphs must be connected. You can use the mic if you want. Yes, but not the same, because here when I have A and B, you talk about this graph, the same graph representation like this. Like this. So you have A, B, after that we make like this. A, B. Yes, not the same, because here the order is not important. I make A, B, but in the sequences I have not this possibility, because I1, I2 have to produce I1, I2 like this, and I2, I1. I cannot use this graph for subsequence or for sequence. Okay. So merging the sequences, if we have k equal to merging two frequent one sequences, I1 and I2 will produce two candidate two sequences, I1, I2, and I2, I1 like I1, I2 like this. So in the first one, I1 is an event, I2 is another event, and the second one, I1 and I2 together represent an event. After that, for a general case, k more than 2, a frequent k minus 1 sequence, W1 is merged with another frequent k minus 1 sequence, W2, to produce a candidate k sequence if the subsequence obtained by removing the first event in W1 is the same as the subsequence obtained by removing the last event in W2. So the resulting candidate after merging is given by the sequence W1 extended with the last event of W2. For example, if we have W1 equal 1, 2, 3, 4 and W2 equal 2, 3, 4, 5, if we want to merge these sequences, the result will be 1, 2, 3, 4, 5, because the last two events in W2, 4 and 5, belongs to the same element. If we have 1, 2, 3, 4, the second example, and 2, 3, 4, and 5 will produce the candidate sequence 1, 2, 3, 4, 5, because the last two events in W2, 4, and 5 do not belong to the same element. So 1, 2, 6, 4, 1, 2, 4, 5, we do not have to merge the sequence, this one and this one. Why? Because the latter is a variable candidate that it cannot be obtained by merging W1 with 1, 2, 6, and 5. Let's move now to another type of pattern mining, but here we will use graphs. So we want to extract frequent subgraphs, and here we have to extend association rule mining to finding frequent subgraphs. So this is useful for web mining or for computational chemistry, for bioinformatics, for special data sets, etc. Graph definitions. Have you an idea about graphs? Do you hear me? Any idea about graphs? Connected edges. So this is what's this? Edge. Okay. And this one. Node or vertex. Okay, so this is the first one is a labeled graph. The subgraph, what is a subgraph? The definition of a subgraph. So a subgraph is a graph formed by a subset of vertex and edge. Yes, we will obtain subgraph from the original one. It is a part. Sub, that means part of this graph. And it is a graph formed by a subset of vertex and edge. So what's the meaning of induced subgraph? So induced subgraph is a subset of vertices plus all edges connecting pairs of vertices. All edges. Each node is connected to all nodes. Yes. Here we have to connect all the nodes together via edges. It is clear? Yes. Representing transactions as graphs. So each transaction is a click of items. So here, for example, we represent the transaction number 1. So transaction number 1 contains A, B, C, and D. A, B, C, and D. After that, we connect all these nodes together with edges. For example, if I have to create the transaction number 5, BCD. B, C, D. Yes. So here we have A, B, C, D, and E. B, C, D. This is the subgraph. Yes. It is clear. Good. Representing graphs as transactions. So here we have a graph and we will represent this graph as a transaction. So we have A and B, P, here A and B, P, here A and B, R, etc. So to represent all these graphs as transactions, we will illustrate all the possibilities. For example, between A and B, we can find P, Q, or R, 3 possible values. And after that, for the first one, we mark 1, 0, 0. For the second one, 1, 0, 0. For the third one, 0, 0, 1, etc. Also the same for BC. For example, here, between B and C, we have R. For this reason, we will mark here 0, 0, 1. It is clear? Okay, so to make graph mining or frequent subgraph mining, there are many challenges. So the first one, node may contain duplicate labels, and there is a problem how we can define the support and the confidence. There are also additional constraints imposed by the pattern structure. For example, the support and confidence are not the only constraints. For example, another constraint, frequent subgraphs must be connected. A priori-like approach is proposed, and this approach uses frequent k subgraphs to generate frequent k+1 subgraphs. So what is k in this case? Other challenges: the number of graphs that contain a particular subgraph. A priori principle still holds. Level-wise a priori-like approach, there are two manners: vertex growing. In this case, k will be the number of vertices, or edge growing. In this case, k is the number of edges. Any questions? Are you here? Okay. So we will study the a priori-like approach with vertex growing and edge growing. Yes? You have a question about the assignment? Yes. Like this. Of transaction, we have to do it for until transaction or only for construct the here the following. Represent the transactions as graph. So you have a transaction. After that, you have to represent this transaction. So, Mr. Abdul Wahid, this is an example like the assignment. Okay, And in this example, we represent the first transaction with a graph. Yes, all transactions. So, for example, for this example, you have to draw 5 graphs. Welcome. Yes, Ahmed. Yes. In the assignment. Yes, construct the inverted index for each attribute value in each dimension. Yes. But normally you can find this in week 6, I think. In week 6. The same mechanism. It will follow the same mechanism. I don't understand your question.